Hello everyone, welcome back to my YouTube channel, Black Box Engineering. I wanted to continue on the technical details of the circuit design. Last video I wanted to explain what impedance is. The technical definition, which probably won't help entirely for people that have never heard the term. It is a combination of resistance and reactance. Resistance resists current, or it limits current in a DC circuit. Reactance is the AC side, where the amount of frequency changes the reduction in current amplitude. So you need both because you need a real part and an imaginary part. It all gets into calculus later on. In simpler terms, though, impedance can be thought of how much passive elements in an alternating circuit reduce or impede the current. Same terminology is applicable when talking about high frequency radio applications or even high frequency digital applications, because they do technically have something in common. They both have a changing voltage in a periodic waveform. Now, a digital circuit does not go below zero, but it still has a very high frequency rate. Some DC waveforms can be manipulated from a DC input into square waves, sawtooth waves, or triangle waves, or anything else that modulates or repeats in a cyclical manner. But the main difference between resistance and impedance is the frequency at which the circuit operates. In a DC current application, there tends to be no frequency, so zero hertz. Disregard clock generation and other oscillators because those are far more complex. For those who have taken circuits, know the general equations for voltage, current, and power across resistors, capacitors, and inductors. But there are more in-depth calculations comes to like the time domain of such things. I'm going to show you those equations. They are somewhat high-level calculus. So let me just switch to my tech forum post here. So the current over a capacitor is equal to the capacitance times the derivative of the voltage of that capacitor over time, and the voltage over that capacitor, same capacitor, is 1 over capacitance times the integral of 0 to some future time of the current of that capacitor in respect to time plus the initial voltage. It simply means that voltage will change over time based off of the current, and current will change based off the change in voltage. It's really simple. The current and voltage over the inductor is kind of the opposite. Voltage over the inductor over time is the inductance times the derivative of current over that inductor over time, over the change of time, I should say. And the current is 1 over inductance times the integral from 0 to some future time of the voltage of that inductor with the change of time plus the initial current measured across that inductor. That probably sounds complex, and it certainly does get very complex when you talk about alternating current, because now that these are included and your voltage signal is now changing, the whole thing gets even more complicated. So rather than trying to do advanced calculus, there is a shortcut called the Fourier transform. I would recommend Khan Academy if you want to learn more about that. All it really does, in very simple terms, it turns complex equations for inductors and capacitors into imaginary or complex numbers, which allows circuits to be solved using the same techniques for basic DC analysis like Ohm's law and other simple methods. Here are the applicable equations derived from the converting to the frequency domain. So I'm going to switch back here. So for impedance of a resistor, and by the way, these are ideal components because it gets kind of really bizarre when you talk about extreme high frequencies, but I'm not going to get into that. So impedance of a resistor is equal to the resistance value. There is no change in equation, really. I had to make a note because modern devices have higher operating frequencies than the little tiny packages. There are still many parts that fall under to the 1 to 3 megahertz range. At lower frequencies, the impedance of a resistor is simply equal to the resistance value. That's what I was talking about before, but it can change based off of much higher frequencies greater than a gigahertz or more. So for capacitors, the impedance of a capacitor is equal to 1 over J, which is the square root of -1. We don't use I in electronics because I also means current, so J is just the format that people went with. So it's 1 over J times omega, which is the radian frequency. So omega equals 2 pi times the frequency in hertz, and then you times it by the capacitance of the capacitor. Another way to rewrite that is to say negative J or negative I times omega times the capacitance. We use angular frequency. Sorry, yeah. Let me correct myself. So angular frequency is omega. We use radians and angular frequency rather than linear frequency because it just works out in calculations that way. So so for inductors, it is the impedance of an inductor is J times omega times the inductance. And again, the same information applies. So each time an AC circuit must be converted before any analysis takes place. Impedance is also measured in ohms. Typically, the J or complex part is omitted when spoken of or written for measurement purposes. An example is an inductor that is 50 microhenries and the frequency of the voltage current source is 1000 hertz or 1 kilohertz. The impedance is calculated as J times 2 times pi times 1000 times 50 times 10 to the -6th, which is equal to 0.314 J ohms, or you could just say 0.314 ohms or 314 milliohms of impedance. Because again, J is assumed in the impedance world. We just don't ever speak it because it just confuses people. So I'm going to go back to my regular screen here. Yeah, so 314 milliohms is that answer. J is the imaginary number is only important when actually used in circuit analysis because it actually determines the phase shift of the AC frequency. So imagine that normally you would start like I think a sine wave starts at 1, goes to 0, 1, 0, 1, 0. But a phase shift just means that that frequency moves to the right or left. It doesn't start at 1 anymore. It shifts a little bit because of how the complex numbers work. It's kind of hard to explain, but it makes more sense if you actually go through a simulation. I probably actually will show you a simulation in the next video, so because I get to talk about frequency filters. So most data sheets list impedance will talk about overall input and output impedance rather than list all the impedance values in a circuit or design. It is the same idea as effective resistance. So determining impedance for special applications such as pulsating DC signals is technically a lot more complicated because it's no longer dealing with AC signals. I mean, I think it's the same equations, but you don't get a phase shift anymore because technically nothing's going beneath 0. But it still applies because you're dealing with pulsating things that are faster, and because things change, capacitors and inductors actually start doing different things. So modern day devices run anywhere from several to megahertz to several gigahertz on the pulsating DC signals. There still needs to be consideration of impedance because of the level of frequency. Design gets as specific as selecting the right cables, making sure that printed circuit board traces aren't too close together, the right value of capacitors, inductors, and resistors along with their operating frequency. The ground plane has to have a special design. Shielding must be applied with very specific materials to reduce electromagnetic interference emission. And then there's a lot more technical details that get into that. So that's just kind of an overview of what impedance is. Again, it's really a quick rundown. There are a lot of technicalities when it comes to the DC pulsating stuff. I never really got into it as in my engineering classes, but I just know the basic concepts to get me by in what I designed. So anyway, thanks for watching, and yeah, let me know if you have questions. In the next video, I'm going to talk about frequency filters and even show you some simulation. I'm using a program called LT Spice. So see you later.